Pleasure to have Yilong Wang from the Quantum Symmetries Group. He joined BIMSA in 2021, so one of the originals. So he will talk to us today about fusion categories and topological field theories. Let's welcome our speaker.
Thanks, Bart. I'd like to thank the organizers for this opportunity to talk. Well, I work on fusion categories and topological field theories, and today I will briefly introduce what I'm doing. So before talking, I think it makes sense to first give an overview. I will review a little bit about the notion of category and then the definition of TFTs, topological field theories. And then there's this construction of topological field theory from modular fusion categories and some of aspects that I'm working on. Okay, so we start with the notion of category. Roughly speaking, a category consists of a set of objects, and to each pair of objects, we assign a set of morphisms. We call this set a Hom set. Although we don't require the objects to have the structure of sets, and we don't know if the morphisms are maps between sets, but we still like to write f from x to y to give us some tangibility of some concepts, because we want morphisms to be composed. We have a composition of morphisms, and we have for each x a distinguished morphism called the identity morphism, so that the composition and the identity are similar to those for maps between sets. So this picture represents a very simple category consisting of three objects x, y, and z, with three morphisms f, g, and g composed with f. This is composition law. And for each x and y and z, we also have this trivial path representing the identity morphism which I omit. So in general, a directed graph can be viewed as a category where objects are vertices and the morphisms are paths between vertices. Okay, so just like directed graphs are abstraction of things and their relations, whenever we want to model something, we sometimes just doodle some graph. A category theory implements this very simple and natural point of view. We understand the world by studying objects and their interactions. But one soon realizes that very often objects are just abstract labels. For example, we have a big polynomial equation, we want to solve it, but we don't know the solution. But we can study the interaction with the solution. That's where Galois theory kicks in, right? So they may not have structures such as structure of a set, and the only way to obtain information about them is through their interaction with other objects. So implicitly imply this, the strict equality doesn't make too much sense in category theory. We usually consider things up to isomorphism, invertible morphisms. Okay. And you may wonder, well, whether studying objects by morphism is good enough to get all the information we need. And category theory says it is good enough. And this is rigorously stated in Yoneda lemma. And the slogan we learned is that an object in a category is determined by all the morphisms from or to it. So for example, even if you have a very concrete category where objects do have a set structure, we still can apply this slogan. For example, I can consider the category of finite dimensional vector spaces over a field, and where morphisms are k-linear maps between these vector spaces. Then for each vector space, it can be recovered by every element can be recovered as a linear map from the base field to the vector space. Okay. Note that in this case, for this category vector spaces, Hom sets, original sets, can also have the structure of vector spaces. Okay, so they are called Hom space later. So in some categories, objects and morphisms can be naturally put together in a suitable sense, and still can be viewed as objects or morphisms in the category. And such category can be viewed as a category with a unital associative binary operation, and they are called monoidal category. So of course, the associativity now are characterized by natural isomorphisms instead of strict inequalities, and they have to satisfy certain conditions. But sometimes these isomorphisms are just obvious, and especially when we use diagrammatic presentation of such categories. So for example, we can consider the category of finite collections of oriented points with morphisms being oriented curves without singularity connecting these points, together with finitely many free loops. we include free loops because we want to sometimes cut in the middle so that we can have parts of cups and caps. So an object you can see is we can just put plus or minus points together, right? And the morphisms are just the collections of straight lines connecting two sides, cups and caps, composing vertically or horizontally. So this is an example of monoidal category where we just put several very simple objects together and get a bigger object. Another, so vectors, the category of vector space has a natural tensor product, which is the tensor product over the base field K. And the associativity is characterized by this canonical isomorphism that we all know. Okay. And then as another example, we can consider the cobordism category where objects are n-dimensional closed-oriented manifolds, and morphisms are equivalence classes of cobordisms, n plus one-dimensional higher manifolds bounding the given manifolds. And the natural tensor product structure is given by this strong union. And in the previous slide, we just showed a morphism in the category called 0 plus 1. Okay, 0-dimensional manifolds are just points oriented, right, and one manifold. And between two monoidal categories, there is a natural notion of maps between them, preserving monoidal structure. And this kind of maps, or rather functors, are called monoidal functors. And now we are ready to already state the definition of topological field theory, or topological quantum field theory. So inspired by the work of Witten, Atiyah proposed to understand topological invariants such as the Jones polynomial in the framework of quantum field theory. Such topological aspects, according to Atiyah, may well be a necessary prerequisite to building an analytical apparatus of the quantum theory. And he proposed an axiomatic approach. So in this talk, n-dimensional n plus one topological quantum field theory, or just topological field theory, is a symmetric monoidal functor from the cobordism category to the category of vector spaces, let's say for simplicity, over complex numbers. The symmetric just means both in the cobordism category and in the category of vector spaces, there's a commutativity. We can switch the order of the tensor product. And the functor has to preserve that. So in particular, we assign objects to objects. That means we assign n manifolds to vector spaces, cobordisms, n plus one cobordisms to linear maps between the corresponding vector spaces. And more importantly, tensor product structure is preserved here. And the empty set is assigned to the base field. Okay, so this is just the definition of topological field theory. So it is very easy to classify TFTs for n equals 0 and 1 because we know this low-dimensional manifolds are very easy. So for n equals 0, they are determined completely by the assignment of a point. That is a vector space. So plus point assigned to a vector space, and the minus point is this 2. So we know exactly what to do. For n plus 1, they are determined by the assignment to the circle S1. So, and in particular, by studying the cobordism category of corp 2 plus 1, 1 plus 1, we know that such assignment to the circle is not only a vector space, it also has a structure of commutative Frobenius algebra. But when n equals 2, things are getting more complicated. We still don't know a complete classification of TFTs. But there's a very important systematic way to construct 2 plus 1 TFTs by Rashtigan and Turayev. They propose that modular fusion categories. So if I have some kind of algebraic input, that's called modular fusion category that we will introduce later, they give rise to 2 plus 1 TFTs. So given a category, I will get a functor. So there are 3 categories involved. One category is your input. The output is a functor connecting to other categories. Really important thing is we assign surfaces, right? Dimension 2, surfaces to Helm spaces of C. So Helm spaces, vector spaces, finite dimensional vector spaces. And because we have a good description of 3 manifolds via link surgery, we will be able to construct such a TFT. So given a 2 plus 1 TFT, we have quantum invariance. That means for closed manifolds, we will have a linear map between the empty set, the vector space associated to empty set to itself, that is just a scalar. So for closed manifolds, we have scalar. And from the graphical calculus of modular fusion category, we can see that we will get not only three-manifold invariance, we will also get invariance of knots and links. In particular, Jun's polynomial can be understood in this framework. And moreover, if you know what mapping class group is, we also have a mapping class group representation. So that I will skip. Well, reciprocal drive TFTs appear in many contexts. For example, in rational conformal field theory, actually the notion of modular fusion category, well, previously called modular tensor category, they are defined in the context of rational conformal field theory, and in the study of topological orders or topological quantum computing, they are also very important concepts. So what is a modular fusion category? So it is a monoidal category that has extra structures and properties. So first of all, we want some linearity because we want to represent the cobordism category to the category of vector spaces. So we want this category to be finite, semi-simple, say linear abelian. That means morphisms between objects are vector spaces, and every object can be written in a suitable way as a direct sum of simple objects. Okay? And for simple objects, we have this Schur's lemma. That means the Helm space is at most one-dimensional. And this finite means we want the number of simple objects to be finite. And of course, the monoidal structure has to be compatible with the linear structure. And we also require the tensor unit of the monoidal category to be simple. What's very important is that the Helm space between the tensor unit and itself is a complex number, so we can get numerical value for things that we want. Okay, we will see later. Now we have a tensor product. We have a direct sum. We can combine them and have what's called the fusion rule. If I have two simple objects, I tensor them together, it's another object. An object is a sum of simple objects, so we can write them in terms of simple objects with multiplicity. Okay, so this is called the fusion rule. And this, let me note that this n, x, y, z are non-negative integers, which are crucial in the algebraic property of modular fusion categories. So before introducing other structures and properties, I would like to introduce this graphical calculus on monoidal categories. It's very intuitive. I have a morphism from x to y tensor z. I just put them as strands, and in the middle I have some picture that I call f. The point is, in the graphical calculus, we want to use suitable pictures for special morphisms. Okay? And we will see that here, for example. So we want some kind of duality in the modular fusion category. And to characterize duality, we not only need a dual object, but also need special morphisms. Remember, objects are characterized by morphisms. So such morphisms give the dual structure. That means I have a special morphism from the tensor unit. There's nothing to draw to x tensor x star, and likewise. Then I can consider the composition of this tensor product of morphisms, and I will be able to draw such diagrams. So this says this cup tensor with identity composed with this cup, the cap before, is the identity of x, and likewise for x star. So that means I can draw strings in the plane, and I can straighten them. Okay, so we can perform topological moves. And we also want the commutativity of the tensor product, which is characterized by the braiding. And we really use the braid diagram to draw the braiding. So from x tensor y to y tensor x. The good thing is, well, we can have a very intuitive understanding of this morphisms. And of course, we want this braiding to be compatible with the associativity. And we always have this identity equals to the braiding composed with its inverse. And that is implemented by Reidemeister 2 move. So Reidemeister 2 is always true, but it's not true that they are always equal to the double braiding. So you can see there's a difference between braiding here. So you can not untangle them.
Yilong, can I ask?
Yes.
If they are equal, do you get a very simple TFT out of it?
If they are equal, then we can completely classify such categories. So they are just given by representation of groups. And the TFT becomes very trivial because there's no linking here. We can resolve any knot, so there's no interesting knot invariant from symmetric categories. And of course, the braiding satisfies Rademacher-3 move, and also known as the Yang-Baxter equation. So remember, when we draw this zigzag picture, I add a remark that we don't have closed loop yet because there's always the star that's not matching. So to be able to, but we always want, of course, we want to draw knots, right, and links. So we want to close diagrams. So in order to close it, we need some extra structure, and this extra structure requires some technicality. But the point is, so there's a automorphism of the identity functor that's compatible with braiding and the duals, so that we can think of our strands. Previously, I draw strand diagrams. We think of the strands flattened into ribbons or bands, so that when we twist it, we see something non-trivial. Okay, so this is a picture of a ribbon that has a non-trivial twist. In particular, algebraically, for simple objects, this theta just is represented by a non-zero number. But according to a theorem, important theorem of Wabpage, this number is very special. It's a root of unity. Okay. So once we are able to close the loop, we have the other cup. We can have something very meaningful. For example, we can define what's called quantum dimension, which is the evaluation of this now closed circle. Okay. So again, the morphism space from the tensor unit to itself is just one-dimensional, so it's characterized by a scalar. Okay? And this scalar is a representation of the fusion rules. That means if you take the dimension of objects, they satisfy the fusion rules. And a theorem of Eddinghoff, Nixon, and Austric says that quantum dimensions are totally real cyclotomic integers. They are integer combinations of roots of unity, and every Galois conjugate of them are real numbers. Okay. So, well, not only we can close very simple loops like previously, we can also close slightly more complicated diagrams. For example, we can close this double braiding. So if the double braiding can be untangled, then we just have two loops, independent loops, right? But now we are not able to untangle them. So this is something non-trivial. But it's still a number. So for a pair of simple objects, we can consider this number and put them into a matrix. And we can also take the theta of x. Remember, I said theta of x is just a root of unity here. We put it in the diagonal. So what can we use it for? So we can put it into a representation of the modular group SL2Z. So if the S matrix, this S matrix is invertible, then we will have a representation of SL2Z. Okay, so that's why we call modular fusion category modular. Okay, so well, we summarize the definition as above. It has the above structures and properties. And there are many examples of modular fusion categories from representation theory. So for example, from non-degenerate quadratic forms on finite abelian groups, where the associated SL2Z representations are just known as the wave representation. And if you are interested in half algebras, semi-simple, factorizable, quasi-half algebras, in particular, if you take the quantum double of semi-simple half algebra, you will get a modular fusion category. And if you're interested in quantum groups as root of unity, you make a semi-simplification, you get the modular fusion category. If you're interested in VLAs, you can consider special VLAs. Or if you're interested in operator algebra, you can consider bimodules of subfactors. All this give interesting examples of modular fusion categories. So this is a very rich world of modular fusion categories. So given the modular fusion category, I can briefly tell you what Versteegen drive TFT is about. So if I have, so I should have F here, because the reason that I don't use MTC now, because people are now studying non-semi-simple ones that have similar properties. So they now call that modular tensor category. So I have to call the semi-simple ones modular fusion. but it's not a big deal here. So I can consider a special object that is x tensor x star. So if you know group representation theory, this is like the regular representation. So a very canonical object that we can consider. Now, for each surface of closed surface of genus G, I just assign the morphism space, a vector space, from the tensor unit to this special object. Okay. And well, what about the? So I need the TFT. So I need to tell you if I have three manifolds bounding two surfaces, what is the linear map? So we can choose a basis for each such morphism space. Then there's a description of any three manifolds with boundary by tangles. Okay. So we have. So the point is, if you don't know this, it's okay. So the point is, there's a pictorial description of three manifolds with boundaries, so that I can draw a picture, and I have, if I choose a basis, I can put the basis on the top and bottom. Then I can view it completely as a tensor diagram from in the category. I can color them, right? I color the red lines by the pseudo object dimension x times x. So I can read it as a diagram in the category. And the top, there's nothing. On the bottom, there's nothing. So it represents a morphism in the Helm space from 1 to 1, which is the C. So this gives me a scalar. And this scalar, I claim, is the matrix coefficient for this cobordism that we want to assign to. Okay. So there's a way to compute it using the surgery description of three manifolds. Okay, so that's a rush course on reticle of TFTs. So there are many aspects of research that we can do on modular fusion categories and also on TFTs. And one of the aspects that I have been working on is the algebraic properties of these categories. For example, I mentioned that this twists, this theta, according to the theorem of alpha, are roots of unity, right? And also this quantum dimensions are cyclotomic integers. So this integrality is very important algebraic properties of these categories. In particular, we have a Galois symmetry. In the following sense, so I consider the S matrix entries. I join them to a big field over Q. Well, it's a finite extension, and you can show. Well, there's this famous Molina formula connecting the S matrix entries and the fusion coefficients n, x, y, z, this non-negative integers. So the Molina formula and the integrality of this fusion rule coefficients implies that for each Galois automorphism, I have a permutation action on the set of simple objects. And this is given by the Galois conjugates of the normalized columns of the S matrix. So I look at the S matrix column associated to Y, and I can perform Galois conjugates to this column, and I will be permuted to another column. So that's what Molina formula tells us. And well, that column corresponds to another simple object because my S matrix are labeled by simple objects. Okay, so that in this way I can get a Galois action on simple objects, permutation action. Okay, and for example, as I said, if you have a finite abelian group and a non-degenerate quadratic form, you can get a modular fusion category, and the S matrix is just the character table corresponding to this quadratic form. And as you can see, here I don't have to normalize because the first entry is just 1, so I just look at the columns. So they are obviously permuted by Galois conjugates. So here I have an orbit with all the zeta 5s, and the 1s are fixed. So I have 2 orbits of Galois action. Okay, so this is a.
Can I ask you something?
Yes.
In the previous slide.
Yes.
So these are these knots? Like, let's see.
Here. Okay.
These are all links. Are these links are kind of knots, right?
Well, they are links. They can be linked.
They can be linked.
Yes. Yes.
So shouldn't you? So let's say I pick an element in V and I pick an element in W, and I'm looking at the tensor of V something picked from V, something picked from W.
No, this V and W are chosen bases. I already fixed a choice of
Okay,
V.
so let's say with respect
yeah.
to, and it's like X and X dual, right? So okay, so I pick something
Yes.
in terms of V, something in terms of W. I
Yes.
want to calculate the tensor product.
Okay.
So shouldn't I not be adding over all possible links that connect them?
So I want to compute a matrix entry. So this.
Right, but this matrix entry, shouldn't it have some counting invariant that counts over all possible red links? Something
So
like
this summation is characterized here.
So that's
so
adding
this
over,
is the sum. So this.
So these x's are
So
what?
so these are already colored previously. Okay. So this x and y's, xi's and yi's are chosen, and these morphisms are chosen. So v and w are fixed, but in the middle you have to sum over all possible things.
That's exactly.
Yeah.
So you are adding.
Yeah.
But then when you are adding,
yeah,
wouldn't that addition should have to do with topology of these braided links? So where is that? Because you're summing over dimension of x.
Yes.
So where do I see the topology of these links?
So
something like Jones polynomial.
So if I have this, right? So I have the sum of dimension x times x. I have some, let's say, dimension y times y. It's really a sum of such individual pictures. Dimension y, sum of this. So I have x, y individually. I compute this, and I take the sum, right? And this is given by the data of the category.
But then this x and y are on the boundary, aren't they?
No, these are labels of labels of simple objects in the category. So I completely put it in the category, compute it in the category. So
okay,
in Jones polynomial, you actually are coloring things by the fundamental representation of SL.
That's right.
So they secretly have
I understand
have a label.
So it is exactly what I'm asking. It's just that I didn't understand the meaning of X.
Yes.
I understand.
Here we have the V2, and in more general categories we have specific labels.
Got it.
That's where we're summing over. Okay. So we have a Galois permutation on simple objects, and actually this can be promoted into a representation of the Galois group of cyclotomic numbers. But well, that group is very simple, but still it's something interesting. But I will skip, omit for now. So one of the problems that I have investigated is modular fusion categories with a single Galois orbit. So previously we saw a modular fusion category with two Galois orbits. So a modular fusion category is called transitive if the Galois group acts transitively on the simple object. Right? There's only a single Galois orbit. And you may ask, are there any non-trivial examples? Indeed, there are. We can just consider a very simple modular fusion category that has two simple objects and has this Fibonacci fusion rule. And why do I call this Fibonacci? Because if you solve x squared equals to 1 plus x, you will get Fibonacci number. Okay? And the S matrix is just given by the given by this golden ratios. Okay? Well, given this S matrix, you can compute the characters, and well, you can try to perform Galois conjugate, and you will see that this category is indeed transitive. So I have -1 divided by d tau, and then 1 is moved to the other. Okay, so we do have a transitive, non-trivial example of transitive modular fusion categories. And with Richard Ng and Qing Zhang, we were able to completely classify all transitive modular fusion categories. And well, we separate the theorem into two parts. First of all, we study transitive ones that are prime, that do not admit non-trivial decomposition. And then they are just equivalent to Galois conjugates of this quantum group at prime roots of unity. And if I want to if I have a general transitive modular fusion category, I just combine these prime ones, but I have to make sure that the order of t's are distinct. Okay, so this transitive, yes. Okay. So finally, I would like to introduce the work with our team here at BIMSA with Zhengwei Liu, Shuangming, and Jinsong Wu. We developed the theory of autofolds in dimension 3, which is a special case of the general autofold theory in all dimensions proposed by Zhengwei, and he will give a talk tomorrow about that. Our work results in a unified language picture language framework for 3D TFTs that subsumes the RT and the TV TQFTs, and their open-closed versions with potential defects. Okay, so let's see be a spherical fusion category. That means it's similar to a modular fusion category. It doesn't have to be braided, but we can still draw diagrams on the sphere. So I consider a so-called C decorated 3 autofold that is consists of a 3 manifold, embedded surface, some tensor diagram on the surface, so that the surface separates M into regions colored alternatively by A and B. Okay. So this is a local picture. I have a surface in the middle. There are distinct regions. And I can have some diagrams on the surface. And we introduce some equivalence relations or moves between among our autofolds. That means we can change the autofold by certain handles. That means I can add 0 handle, 1 handle, 2 handles to the autofold to change the color of the regions. And so once we do that, we will reduce the topology of the B color region to a disjoint union of balls with tensor diagrams on their boundary spheres, and we can evaluate such diagrams. Okay. And well, we can, after evaluating this diagram, we get a number. But our theorem says that there's a unique optoscalar partition function from autofolds to C, such that it's invariant under homomorphism of autofolds, and the autofold moves, and its multiplicity with respect to disjoint union is independent of the topology of the A color region, and it extends the spherical graphical calculus of the original category. Okay. For 3 manifolds, this handle decomposition are closely related to triangulation, and maybe you have heard of this. We can, from a triangulation and a category, we can get the so-called trioviro invariant by attaching 6G symbols to tetrahedra. And we are able to show that if my closed manifold is completely B colored, there's no surfaces or no diagrams, I will recover the trioviro invariant. And what about the A color? So the A color part corresponds to the Drinfeld center of C, which is a canonical modular fusion category associated to my category. I will skip this because it's a bit technical and I don't have too much time. So the point is, I can use autofold moves to prove that the trioviro invariant for C is equal to the Rashid trive associated to the Drinfeld center of C, okay, given by a surgery if my manifold is described by a link surgery on S3 over S3. Okay, so our main theorem is that our autofold invariant extends to a TFT. So we have a suitably defined autofold cobordism category. We have a symmetric nodal functor from this cobordism category to vector spaces, and we have the Rashid trive TFT is the same as trioviro TFT as the same sub-TFT of the autofold TFT. Okay, so this equivalence has been studied for more than a decade and was established by technical methods by many. And our proof is intuitive and topological in nature, and both on the level of 3 manifold invariance and on the TFTs. And autofold theory allows us to compute, allows computations involving both C and the Drinfeld center of C to take place in a uniform, unified framework. And this allows us to easily establish the S2Z invariance of the generalized Frobenius-Schur indicators. So let me finish by some outlook. So there are 2 parts that I talk about for fusion categories and TFTs. The first is study modular fusion category from algebraic structures of properties. And one important thing is to study them using their SL2Z representations. And the important fact is that these representations factor through SL2Z mod NZ. And such representations are completely classified, and we have written a gap package to implement such representations. So this helps us to classify modular fusion categories. And well, not all of this such representations can be realized by modular fusion categories. Some necessary conditions are explored by us, but we are stuck at a certain number of theoretical problems. So if you have experience in prime factors of closed term sums, please let me know. So we are stuck for 2 years. Okay. So SL2Z representation is just one aspect of the mapping class group representation associated to TFTs. So we can also study higher genus representations of the mapping class group. And also, speaking of algebraic structures, there's a natural group associated to modular fusion categories that generalizes the weight group of quadratic forms, and I have done several works on them. As for autofold theory, we have established the TQFT and the Morita equivalent spherical fusion categories, allowing even more diagrams and defects to be computed at the same time. And this covers, in particular, the theory of modular invariance and alpha induction. And there are more to explore in this direction. And finally, there's this non-semi-symbolic TQFT that to be explored. So that's it, and thank you.
Thank you very much. Any questions?
Thanks, Yilong. So I want to ask about the unitary or the pseudo-unitary case. Is there any special things that happen?
Well, for unitary ones, we in our autofold we have this reflection positivity, so we can, But in general categories, you don't have that, so it doesn't really it's not really clear what would you have if you flip the diagram. But in unitary cases, it has a specific meaning. Mm-hmm. Yeah.
Because from the physical point of view, like the reflection positivity is like very important.
Yes.
So and maybe one can hope to construct like a field theory of some kind, in which I get autofold TQFT.
Yes, in autofold TQFT, you can also study lattice models and things like that. So they are very convenient.
Yeah.
Yeah.
Mm-hmm. Okay.
Any more questions?
Why did you need Deligne product?
For what?
That's a statement that you proved. You were looking at.
So we first show that the categories that we study have a decomposition into Deligne products. Then, so this is natural. So you can build monodic categories, tensor categories from Deligne products, right? And then, they're just simple as that. You don't have some mixed things in between, so they're just strict Deligne products of simple ones.
Okay. Another naive question is this. So when you calculate these three manifold invariants, so there are some instances where, well, you're mainly discussing Witten, Reshetik and Turaev invariant, but I'm interested in Witten, Reshetik, and Turaev invariance for three manifolds because it actually connects to algebraic geometry.
Okay.
And there are some instances where you can cook up artificially some situation that the partition function of these WRT invariants is a modulo 4. For example, the three manifolds you get by topological plumbing of Briskern homology spheres has WRT invariant partition function, which is modulo form, exactly with respect to SL2Z action. So do you get these kind of invariants in this general setting where your partition function
I think if I
is modular?
Specialize to SL2 level K, I do get.
Always?
But for higher rank ones, for other modular tensor categories, I don't think it's studied. But probably there may be some modularity also. Yeah.
Do you have proved such thing?
No.
No. Is anyone guessing it or no?
I think there are people working
like other than this topological plumbing of Briskern homology spheres, do we have partition functions of three manifold invariants in general that have
modular form?
Yeah.
Well, I think when we, so first of all, if I give you a modular fusion category, I give you a 3-manifold, you will only get 1 number, okay? But when you have this plumbing, then you can have a generating series,
Right.
right? This is what you're talking about. Then, in general, I'm not sure. I haven't thought about that. Yeah.
Okay. Yeah.
Any more questions? Could you go to slide 14, please? I saw the word
14.
representations. So I want to ask something.
Okay.
So so I saw the word quantum group. So G is finite dimensional simple Lie algebra here.
Yeah.
Right.
For simplicity, yeah.
So can you do it more generally,
Can we do it more generally?
or since you said for simplicity?
Well, I guess just simple Lie algebras.
No, there's lots to be done there, I guess. So do you know what a semi-simplification is in every case here? Like, is it a concrete thing that is known, or do you have to do a particular type of semi-simplification?
Take tilting modules and take mod out the negligible, that kind of thing. Okay. I think K may not need to be integer.
Okay,
yeah,
rational number?
Yeah, some rational number are allowed, and for some rational numbers, they definitely give you very non-unitary things. That's very interesting. So that's an aspect.
So I suppose I could also replace this with something like Lie algebras over a field of positive characteristic, and of some instead of quantum.
Yeah, I guess so. But I don't know. Maybe you can take the double of restricted Lie algebra, but whether or not that has a ribbon structure, I'm not sure. Maybe they do.
Yeah. Final question. You can do a la Kruijsdal-Lustig, maybe go to affine Lie algebra level K representations.
Yes.
Is this kind of, can you translate from the quantum groups at the root of unity to that, or?
I think so.
In your construction, I mean.
The book of
in your construction.
Sokolov and Kirov. Yeah, says something about that. Yeah.
Cool. Okay. So we're kind of out of time, so let's thank our speaker.
Thanks.